In this problem, we're being asked to integrate x squared minus 16 to the power of 3 halves divided by x. Of course, to solve this, we need to determine which integration technique would be best. We'd usually start out with a u sub, but u sub doesn't really seem to work here, right? So if you chose u to be the x squared minus 16, which presumably is what we would choose, its derivative would be 2x, but that 2x would not get produced in the denominator, right? The 2x would have to be kind of in the numerator alongside the dx. So u sub doesn't really work here, but instead, I might be inclined to do an integration using trigonometric substitution, right? So we see that there's this x squared minus 16. It's also got a root, which is like a typical situation we might have when we're trying to do trig sub, but in particular, it kind of fits that form, right? Something squared minus something else squared. That kind of looks like secant rule, right? So when you think about secant, inverse trig function, its derivative and all that, that's kind of what you're getting. So over here, I'm going to go ahead and make the choice of x to equal 4 secant theta. Again, secant because I'm going to try and fit it to secant squared minus 1, an identity, Pythagorean identity there. And I'm going to choose 4 because I want to square it so it matches the 16, and I can factor that out. Okay. I'll also do dx, so I'll have to replace obviously dx if I replace x's. Dx would be 4 derivative secant is secant theta tan theta. And so what we'll do is we'll take this and we'll go ahead and plug in and see what our integral comes out to be. So what do we get? We get integral 4 secant theta squared. I'll just write everything out first, and then we'll go ahead and simplify as best we can over 4 secant theta. Then we'll multiply, right? Our d theta gets replaced, so you multiply by 4 secant theta tan theta d theta. Right? So replace all the x's and replace the dx. Now at this step, we'll go ahead and try to simplify the best we can. So I'll cancel out a 4, I'll cancel out the secant, then I'll go ahead and try and tackle this. So here, 4 squared would be 16, 16 times secant squared, 16 secant squared, and then minus 16. This is all to the power of 3 halves. And then there's no denominator anymore, right? So we've gone ahead and basically removed that bottom portion, and then we're multiplying by tan theta d theta. Again, tackling this, remember 3 halves is the same thing as this root cubed. And so I'm going to go ahead and take this, pull out the 16 first, right? So we'll do this as an intermediate step, pull out the 16, secant squared theta minus 1. That becomes 16. What's secant squared minus 1? Well, remember 1 plus tan squared equals secant squared. So secant squared minus 1 would equal tan squared. So we're looking for tan squared there. And then all of that was to the 3 halves, right? So 3 halves. In this case, I'll rewrite that 3 halves as a root. So here we're going to have this cubed. Then I'm going to take the square root of this. Square root of 16 we know is 4. Square root of tan squared is tan. And then we're going to be left with that thing cubed, right? So we have this. This is kind of an intermediate step, and then this other integral would then equal integral 4 tan theta cubed tan theta d theta. Okay. So 4 cubed, we could go ahead and do that, right? 4 times 4, 16 times 4 is 64. And then you have 3 tangents, and then you get another tangent. So in total, we've got 4 tangents. Okay, now at this step, I need to figure out how in the world do I integrate tan to the power of 4. Well, I don't know how to integrate tan to the power of 4, but I suppose the question in our head is, do we know how to integrate tangent squared, right? That seems to be an identity or something that we might know. So split 4 into a tan squared and tan squared. And then I also know that tan squared is, well, think about the identity we did over here, right? Tan squared is secant squared minus 1. So what if I did something like this, tan squared, secant squared minus 1? Distributing this out, we get tan squared theta, secant squared theta minus tan squared theta. And so the integral we're really trying to do is 64 integral of tan squared theta secant squared theta minus tan squared theta d theta. Now, looking at these, obviously we need to figure out how to do our integral. So right here, this looks like a good opportunity for a u sub. The reason I say this is because the derivative of one of these trig functions is in the problem, right? So if I were to let u be tangent of theta, we easily see that the derivative, secant squared theta, is in the problem, right? It's right here. So we could handle this portion of the integral with a u sub. However, the other portion, what do we need to do here? Well, again, I don't know how to integrate tangent squared, but I do know that if I split this up using our identity, which is secant squared minus 1, I can integrate secant squared, right? So the derivative of tangent is secant squared. So this integral would be relatively easy to figure out. And then the integral of 1, also relatively easy to figure out. It just becomes theta. So all in all, let's go ahead and write this out. It might help us to split these integrals up just so we can show that process. But let's kind of pull this here. So we get integral 64 tan squared secant squared. And then I'll subtract 64 secant squared theta minus 1. Now, of course, again, we do the u sub on this. So this becomes u squared. This becomes du. Over here, this secant squared just goes to a tangent, and this goes to a theta when we integrate it. So on our left integral, we get 64 u squared du, which becomes 64 u cubed over 3. And then if we want to go ahead and simplify this a little bit more, 64 over 3 u cubed du. U is tangent, so tan cubed theta. Now, tackling the second integral, right? So subtract 64. Secant squared, we said, goes to tangent. 1 goes to theta. And then again, these are all indefinite, so there will be some plus c at the end. You can throw it on whenever you want, so that'll handle kind of this plus c for now, and then this will just get attached to this plus c, right? Everything's just a constant. Here, repeat this all the way down, and then we get this. Okay, so now recall our original integral. So if we go all the way up, we're integrating something with respect to x, right? So this integral had x values in it, and we did this substitution for 4 secant. I now have kind of a solution, but it's in terms of theta. It's not in terms of x. And so what I need to do is I need to bring it back to be in terms of x. The way to do this is we're going to go back to the original substitution, and we're going to make a triangle to solve for tangent and theta itself, right? So we're going to find tan theta and theta. So let's go up here. Think about our substitution. X is 4 secant. This tells me then that x over 4 is equal to secant theta, which tells me that cosine theta, which is secant's reciprocal, would be 4 over x. Therefore, if you make a triangle, and I make my angle theta be here, cosine, which is adjacent over hypotenuse, would be 4 and x here. The opposite side, right here, typically this is always going to be a value that matches kind of where your problem was. So if you look back in your problem, you'll see, presumably most times, the term here. So in this case, whether you, again, look here or you do Pythagorean theorem, we could easily do this for a right triangle. You would get x squared minus 16. Okay. And so with all this being said, remember that we were trying to find tangent of theta for our substitution way down below. So what would be tangent here? Well, tangent is opposite over adjacent. So tangent would be the root, x squared minus 16, all divided by 4. And subsequently, theta could be any version of what you want. Maybe you'd use secant inverse, right? So we could do secant inverse of x over 4. That would work well. You could also use this tangent relationship and just do a tan inverse. So we could do tan inverse of that over 4. You can kind of decide how you want to do this. It really is a matter of preference, but they all correspond to the same theta, right? The same angle. So let's bring all this down here, right? Again, tangent is this, secant is this. So we'll try and plug this in. I'll write this on the side here again. So our tangent, we said, was root x squared minus 16 over 4. And then we said theta could be any combination, right? I might use secant inverse of x over 4 here. Therefore, we'll plug this in, right? What would be my final outcome? Well, I'm going to get 64 over 3 tan theta, which is x squared over 16, x squared minus 16 over under the root, divided by 4. That'll be cubed. And then I'm going to go ahead and subtract 64, same deal, root x squared minus 16 over 4 minus secant inverse x over 4 plus c. And then if you want to simplify, you can. Here, 4 cubed would be 64. That'll actually cancel out with this 64. So I should be getting a 1/3. And then for simplicity, I'm going to rewrite this back to be a 3/2 so it doesn't look a bit messy. Back over here, 64 and 4, you can multiply that out. So that'll be 16 with the root x squared minus 16. And then the 64 can distribute here as well. 2 negatives make a positive. 64 secant inverse x over 4 plus c. And that would be our final answer. Note again here that we could have replaced this to be the theta in terms of arctan or tan inverse. That way, I don't know if that looks better, or if you look this up and you're trying to see if these things compare, remember that there is multiple versions of the representation for that theta, right? I can use secant inverse, I can use tan inverse, I could use even cosine or sine inverse. There's all the different trig functions we could have used. Perfect, there you have it.